Welcome everyone, my name is Szabolcs Hack. I am a research fellow at the Eli Alps in the Theory and Simulation group, and I'm going to talk about our latest results in the topic of strong field ionization and the real classical picture behind this process. In the last few years, many groups published their experimental results in strong field ionization and on the characteristics of tunneling process. It is not fully understood what measurement technique is worth performing the measurements and exactly how the result should be interpreted. But obviously, there are quite a few things in common in these measurements. What do they have in common? They measure non-zero exit momentum of the ionized electron in the range of few tenths of atomic units. They measure also non-zero time interval between the main peak of the laser pulse and the instant of the liberation process. It is called often tunneling time or tunneling time delay. There is a measurement about the starting position of the escaped electron, which is 5 to 10 atomic units. For the most experiments, the Keldysh parameter is around 1. It causes that the ionization pathway is non-trivial, so we cannot think it's a pure tunneling ionization. The theoretical explanation of these experiments is still lacking. The traditional tunneling picture stays in contradiction with the conservation law of energy in case of non-zero exit momentum. So this is our starting point, and let's see where we get. We want to introduce new type of classical trajectories to approximately model the strong field ionization and at the same time to explain the experimental results and to avoid the contradictions. On one hand, it is intuitive to use a single point of the quantum momentum function as the initial momentum of the classical propagation, since it is the position-dependent average momentum of the quantum particle in a sense, and which can be derived from the Wigner function of the quantum state. On the other hand, the blue curves are the stationary phase-space trajectories of the instantaneous potential corresponding to different energy values. In fact, there are uncountable trajectories because the energy is a continuous parameter. So all these trajectories have an outermost inflection point somewhere here. And beyond this point, the quantum propagation can be very well approximated by classical dynamics. So taking into account both of the previous arguments lead us to a unique point in the phase space at every realistic starting time, because there is always only a single energy values when this equation is satisfied. So we propose the here defined phase space point as the initial state of the classical escape trajectory. And since the initial kinetic energy of the classical propagation right after the liberation quantum process is always positive, due to the quantum interference of the ionization pathways with different energies, these are detailed in this paper, this model fulfills the energy conservation law. Now we want to compare the real quantum process with our classical model. We'll use a simple physical system, a hydrogen atom in dipole approximation, which interacts with a 3-cycle linearly polarized laser pulse having the peak intensity of around 100 terawatt per square centimeters and the central wavelength of 800 nanometers. For these parameters, the Keldysh gamma is below but close to 1. Since the main part of the dynamics happens along the laser polarization, we compute the 1D reduced density matrix of the electron's quantum state along the z-axis, along the polarization axis, from the wave function by integrating over the azimuth angle and the radial coordinate. And from this reduced density matrix, we compute the electron's Wigner function, which helps us to visualize the quantum dynamics on phase space. Now we are able to compare the classical and quantum dynamics. The red dot here represents an electron, which is escaped at this moment. The red curve is a stationary phase-space trajectory of the instantaneous potential, and the black solid line is the quantum momentum function. The color scale of the Wigner function in the background is logarithmic. During the time evolution, we can see that a small part of the Wigner function and also the quantum momentum function is close to the classical electron. But it is only one classical trajectory of the many possible, and the good classical model have to also reflect that the liberation process is blurred both in space and time. We plot here several phase space trajectories shown by dashed lines and the electrons represented by dots. Compare them with the quantum momentum function represented by black solid line at some characteristic snapshots of the dynamics for different starting time instants. The electron is close to the quantum momentum function during the whole propagation, regardless of the starting time, which well justifies that they represent a good classical approximation of the true quantum dynamics. We can see as the starting times get closer and closer to the instant of the main peak of the laser pulse, closer to 165 atomic units of time, the electron does not have enough kinetic energy at the end of the interaction to leave its parent ion permanently. For further increasing starting time, the electron is rescattered with energy gain from the laser pulse, and it may thus contribute, for example, to high harmonic generation. I would highlight that the starting position and momenta are in very good agreement with the experimental results mentioned a few slides before. On this next figure, we can compare our new trajectories marked with dashed lines with the improved Simpleman model marked with solid lines. The trajectories of the improved Simpleman model start at the instantaneous tunnel exit with zero exit momentum, and in addition neglecting the Coulomb interaction. The curves with corresponding colors starts at the same starting times. It can be seen that the starting time interval corresponding to direct ionization and the starting time interval corresponding to rescattering is very different from each other in the two models. And for the Simpleman model, the rescatter trajectory during the interaction is missing. Using our classical model, I show a simple procedure to reconstruct the starting time of a directly ionized electron from its detected momentum. The steps of the iteration process are the following. First, we calculate the final momentum of the electron on such a trajectory which starts at the same time but neglects the Coulomb interaction. We calculate this from the measured momentum and from the input parameter of the iteration, which is the initial coordinate. Secondly, we calculate the starting time of the classical propagation. P tilde 0 indicates the average value of the possible initial momenta obtained from the simulation. Thirdly, we calculate a new starting position with the T0 obtained in the previous steps and with this analytical formula for the inflection points of stationary phase space trajectories of the instantaneous potential. With the obtained initial position, we start the iteration cycle from the beginning, and after 4 or 5 cycles, we get a convergent result. In this table, we summarize the accuracy of this iteration procedure. We performed numerical experiments, so we generated the detected momentum values according to our proposed initial conditions. You can see here, in case of different electric field strength, the real starting times and positions, and the reconstructed ones marked with capital R. For the really probable trajectories, the error may get even below 5 attoseconds. We tested the reconstruction procedure for different carrier envelope phase differences too. The accuracy and the tendency of the procedure does not change by changing the CEP of the laser pulse, and the reconstruction works well for the liberation processes happened around the 2 main peaks of the laser pulse, such as in case of a sine-type laser pulse. In conclusion, we saw that a set of new classical trajectories give a good classical approximation of the true quantum dynamics. These trajectories solve and explain the problem of non-zero initial momentum comes from the traditional tunneling models, and based on our new initial conditions, we gave an iteration procedure to reconstruct the initial parameter of the classical trajectory.